Okay, the last two examples in section 3.3 are going to be about pulley problems that have friction in them. Now these are still frictionless pulleys. What that means is that there's no friction in the actual pulley, as in this part right here is frictionless still. Now what that means is something that we're not going to worry about yet. But there are problems in physics where there's actually friction in the pulley, and that's going to affect how the pulley actually rotates, and we're not on rotation yet. So when I say pulley problems with friction, I mean that there's friction somewhere else in the question. So in this case, there's friction right here. That's going to act against the motion of the pulley system. So we'll look at one here on a flat table, and look at one on an incline, and let's get into it. So I never plug in numbers until the end, so the first thing I'm going to do is give the blocks names. So I'm going to call the block on the table block M1, and the other block M2, because it's the bigger mass. This is a forces question, so the first step is to draw the free body diagrams. So I'll start with the smaller block on the table. The first forces are acting in the y direction, so the block is pushing down on the table, and the table is pushing back. So that's the normal force in gravity. Now this smaller block's moving in the x direction, so you would think the y direction doesn't really matter here, which it really doesn't, but the normal force is what determines how strong friction is, because friction is coefficient of friction mu times the normal force. So just looking at the y direction here just for a minute, the sum of the forces in the y direction, because it's not moving in the y direction, it's moving in the x direction, the sum of the forces in the y direction is 0. So then normal force equals the weight of the block, which is m1g. We're going to use that later when we look at what the force of friction is. Okay, so the force pulling the block forward is tension in the rope, which I'll call T. And then since it's a rough table, there's friction. It's moving to the right, so there's friction to the left. Okay, now I have my picture. I'm going to do F equals ma in the x direction, which is the direction of motion. Tension will be a positive force because it's pulling it in the direction of motion. And then friction is a negative force because it's acting against the direction of motion. Okay, so there's the equation. As I said, tension is positive, friction is negative, equals ma, and this is m1a because it's just for block 1. And then the force of friction is mu times the normal force. This is why I found out that the normal force was the weight of block 1. Okay, and there's my first equation. So I have one equation. This is a pulley question, so I need two equations for both blocks. So the second block is a lot easier. There's only two forces on it, which are tension and gravity. Okay, now for this one, it's moving down. So in this case, force of gravity on block 2, that's in the direction of motion, so it's positive. And then here, tension is negative, because it's acting against the direction of motion. There's what that looks like as an equation. So the forces on block 2 equal m2a, because this is just for block 2. m2g is positive, and tension is negative. Okay, now I'm going to add the equations together. And you can see that tension is positive here and negative here, so it will cancel out. For any pulley question, if you're doing the two blocks separately, tension does have to cancel out. It's an internal force, so it doesn't affect the motion of the system. m2g and friction are external forces, so they do affect the acceleration, but tension's internal, so it can't affect the acceleration. So tension's an internal force. An internal force doesn't affect acceleration, only external forces do. This video shows the guy in the truck. He's an internal force, and the dudes outside are external forces, and they can actually affect the acceleration. After canceling out the tensions, I get this equation down here, and the left side has acceleration in both terms. I'm going to factor out acceleration, and I get this equation right here. Now, how I started this question, and how you should do it as a Physics 1 student, is I considered the two blocks separately. I did the free body diagram for both blocks, then did F equals ma in the direction of motion for both blocks and added the equations together, and the internal force canceled out. Now, another way to consider this system is, okay, I have a combined pulley system with a total mass of m1 plus m2. So the total mass times the system acceleration equals the sum of the external forces. So tension was an internal force. Gravity on block 2 was an external force. It's in the direction of motion, so it's positive. And then friction on block 1 is another external force, and that's against the motion of the system. So what I have there is F equals ma for the system as a whole. So I have, again, acceleration times combined mass equals the sum of the net external forces. Right? Gravity is an external force because it's the Earth pulling on the block, and then friction is an external force because it's the table acting on the other block. Tension is the internal force and didn't affect the acceleration at all. Okay, now when I divide by the mass, I get an expression for the acceleration, which is what we're looking for. So all that's left to do is to plug in numbers. So when I plug in numbers, I get 4.8. So that's the acceleration. So the block on the table accelerates to the right at that rate, and the block hanging off the table accelerates down at that rate. Okay, and that was a Pulley question with friction. So it seemed kind of scary at the beginning, but it really wasn't that difficult. I just did a free body diagram for both blocks, did F equals ma in the direction of motion for both blocks, so that was the x direction here, and the y direction here. The internal force canceled out, and I eventually got the answer. Okay, last example is example G, and there's a lot going on here. We have a pulley system, there's an incline involved, and there's friction involved. So it's kind of a complicated question, but if you do what you're supposed to do, it's not that hard. And that's draw a picture, label the forces, and then do F equals ma in the direction of motion. So for the direction of motion, the small block's going to move up the incline, and the bigger block's going to go straight down. So I'm going to start off with the free body diagram for both the blocks. So the small block M has the more complicated one. It's being pulled uphill by tension. So that's going to be the positive force for this smaller block. And we have gravity acting directly down. And it's on an incline, so I have to put components of gravity. There's the part acting into the incline, which is mg cosine theta. And the part acting downhill, which is mg sine theta. And then it's being dragged uphill, so friction is going to act downhill for this block. And last, the normal force. Of course, the normal force is not in the direction of motion, so it won't affect the motion directly. However, the force of friction is based on the normal force, so the normal force cancels in the perpendicular direction with mg cosine theta. So the force of friction is going to be mu times mg cosine theta. Okay. Now the bigger block has a very simple free body diagram. Its weight, mg, goes down, and tension goes up. Okay, so now I do F equals ma separately for both blocks. So I'll start with the hard one, which is the smaller block. So the sum of the forces equals little m times a. And then I have three forces in the direction of motion. I have tension acting uphill, friction acting downhill, and then mg sine theta acting downhill. So that looks like this. Tension is positive, mg sine theta is negative, and then friction is also negative. And I'm going to replace the force of friction here with mu times the normal force. So I have mu, the coefficient of friction, times the normal force on an incline, which is mg cosine theta. Okay, so that's my first equation. And the other one's a lot simpler. The sum of the forces equals ma. Now for this one, the direction of motion is down. So in this case, tension's a negative force, and the weight's a positive force. And that's the second equation. Now I'll come down here and add them. And again, the tension has to cancel out. Which it will. Okay, so on the left I have ma plus ma, they're different m's. And then on the right I have mg, which is the positive force, that's dragging the pulley system down. down over here. And the two negative forces, which are the weight of the small block acting down the incline, and then force of friction on the smaller block. Okay. Then if I factor out the m's, or if I factor out a, if I factor out a and divide, here's what I get. And I'm not going to show how to plug in numbers here, but everything in this equation is given. Little m is 5, big M is 10, theta is 30, and then the coefficient of friction, which is mu, is 0.2. When you plug in numbers here, you get 4.4.